Okay, the answer to number one, basically, when we're swinging that rock on the end in large circles, essentially it's because the rock is in motion, constant motion, um, and uh, the rock has mass. Even though Earth is attracted to the sun by a very strong gravitational pull, which keeps the fact that Earth moves. It both moves by spinning around the sun and spinning independent of the sun. Why does the moon strike the Earth? Again, it's moving. And because those electrons are moving. It's the old Incredibles effect. Violets. So wavelength is measured in meters, and frequency is measured in hertz, or what is called an inverse second. 2 hertz versus 4 hertz. There's 2, and then this one would have twice as many humps because it is more frequent. These are the smaller steps back to our lab. As the frequency of light increases, what happens to the wavelength? If the frequency goes up, then the wavelength must go down. In other words, if I come back here and I measure these versus these are bigger and these are smaller. And the relationship is an inverse relationship. And so if we said for every 3 times 10 to the 8th meters, light has a frequency of 1 hertz. If the new wavelength is 6 times 1 over 10 to the 8th, we'd be multiplying by 2 times 1 over 10 to the 16th, which means here we'd be dividing, because this is an inverse relationship, by 2 times 1 over 10 to the 16th. 1 divided by 2 is 0.5 times 10 to the 16, positive 16, and we can kind of check this answer. This number went way down, and this number went way up, which matches our relationship. And then number 10 says, well, what if we have, and I didn't leave myself a lot of space here, we know that 3 times 10 to the 8th meters, there is 1 hertz, or 1 frequency. So if the frequency was more frequent, this is 4 times 10 to the 14th. This number is getting much bigger, so we'd be multiplying by 4 times 10 to the 14th, which means over here we'd be dividing by 4 times 10 to the 14th. So 3 divided by 4 is 0.75, and then 10 to the 8th divided by 10 to the 14th means that we'd be left with 10 to the 6th on the bottom meters. And the units for energy and frequency, energy is measured in joules, not Marianos, joules, and frequency is measured in hertz. As the energy increases, what happens to the frequency? So if you think back to your little steps, when we had smaller steps, we used more energy. So when they became, in other words, when they became more frequent, it meant that we used more energy. So the graph would look like that. And of course, on the last page, this is a direct relationship. As your steps became more frequent, you used more energy. So that looks like a direct relationship. Does an electron need to absorb energy or give off to go from the first to the second energy level? Well, we're being promoted, or to go from the second to the first, sorry. So in order to go from the second to the first, it would need less energy, not less speed, because it's moving in closer by the nucleus. How is it possible for the energy to go from third to fourth? So if we're promoting it, it needs more energy, which is different. It is not more speed, which is what we always think. For red light is a frequency of 4 times 10 to the 14th. How much energy is the electron gain from the light? Well, we know that for every 1 photon, there is 6.5 times 10 to the negative 34th joules required for 1 hertz. And I just shortened this to 6.5 and 6.63 on the other page. So we have 4 times 10 to the 14th hertz. So to get from here to here, we're multiplying by 4 times 10 to the 14th. But if I look back up here, I notice that that graph is a direct relationship. So that means I'm going to do the exact same thing. And I know we got in the habit of doing something different. So we got 14 tons on the top, 14 tons on the top, and we got a 34 tons on the bottom, which means that's going to result in us having 20 tons on the bottom. And 6.5 times 4 is 24, 26. So 26 times 10 to the negative 20th. The energy difference between the first and second energy levels is 3.3 times 10 to the negative 19th. What frequency of light is necessary to get to that? So we're going to use the exact same constant that we had. So 6.5 times 10 to the negative 34th joules. 1 photon has 1 frequency, or 1 hertz. So this is going to be 3.33 times 10 to the negative 19th. So this number is getting bigger. So we're going to multiply by, it's about a half, times 10 to the 15th. So we got 15 tons on the top and 34 tons on the bottom. And 6.5 times a half would give us about 3 and a half, 3 and a quarter. So that's close enough for our purposes. This is a direct relationship because the graph for energy and frequency looks like that. So this is going to be times 1/2 times 10 to the 15th. So this is 0.5 times 10 to the 15th. And on the last page here, again, we were looking for frequency. So we're going to say 6.5 times 10 to the negative 34th joules. There is 1 hertz per photon. And we'll talk more about this next week, conceptually. I just need to be able to have you do the math here. So this is 4.05 times 10 to the negative 19th joules. So we're going to multiply by a fraction to get this number to be smaller. So that fraction is about 2/3 times 10 to the 15th. Direct relationship. So we're doing 2/3 times 10 to the 15th. So we get 0.67 times 10 to the 15th hertz, or 6.7 times 10 to the 14th, or 670 times 10 to the 12th, and then we could change this to a prefix. What wavelength does this correspond to? So now we got to think back. So it's 3 times 10 to the 8th meters. There is 1 hertz. And so we could say, all right, well, this is over here, 670 times 10 to the 12th hertz. So this number is getting way bigger. But remember that this is an inverse relationship. So we're going to divide by 670 times 10 to the 12th. So 3 divided by 670 is, I know 0.67 is 2/3. So that means 670 is 2/3 times 1,000. which means that when we do the inverse of this, we're going to end up with 3 over 2, 6 over 2, which is 3 thousandths, times, we got 10 to the 8th divided by 10 to the 12th, which means we're going to leave 4 tens on the bottom. So this actually comes out to be about 3 over 10 to the 7th, or 30 over 10 to the 6th. So do atoms of different elements have different numbers of electrons? Yeah. Spent a few weeks talking about that. And that impacts the color that they have. If all of the electrons of atom A get excited and then lose all their energy and return to the ground state, so in other words, if we got a nucleus and we got an electron here, it's going to jump down to the ground state, back to its original energy level. Combination of frequencies and colors of light. Each frequency and color corresponds to a specific electron making the transition from excited to ground state. Consider an atom from element B. Would you expect the excited electrons to give off in the same color as atom A? And the answer there is no, because these electrons are all different and they all have different amounts of pull that they feel from the nucleus, because that nucleus, if they're two different atoms, then they have different numbers of protons. So the pull that they feel from the nucleus is very different. And so the amount of energy that they give off or need to absorb to jump levels is very different.